Hi, welcome to the audio slide presentation of our recent paper. I'm Pavlo Stefano from the University of Cyprus, and for the next few minutes, I will be discussing the results of our paper, The Rheology of Drilling Fluids from a Non-Equilibrium Thermodynamics Perspective, published in the Journal of Petroleum Science and Engineering in 2017. Drilling fluids are usually suspensions of plate-like particles, such as bentonite, saponite, and sepiolite. The most common clay used is bentonite, which is largely composed of the mineral montmorillonite. Their use in drilling operations is multifunctional, including removing rock from the hole, cooling and cleaning the bit, lubricating the drill and the bit, etc. For drilling fluids to bear the capacity to perform these crucial functions, their rheological properties should be finely tuned. The ineffectiveness of drilling fluids to perform any of the above-mentioned functions leads to several drilling problems, resulting in enormous financial losses. The rheological behavior of drilling fluids is usually described by simplistic constitutive equations, such as the Casson or the Herschel-Barclay models, all of which exhibit a non-vanishing yield stress, i.e., flow will occur only when the stress exceeds the yield stress, and the power law model. Despite the overwhelming data highlighting the significance of their use in numerous fields, they fail to produce normal stresses, whose importance in drilling operations has only recently attracted attention. The successful prediction of normal stresses, and not just shear viscosity, is paramount if optimization of drilling operations is to be sought. In this paper, we introduce a continuum model for predicting the rheological behavior of drilling fluids with plate-like suspensions based on the Hamiltonian formulation of transport phenomena for fluids with a complex microstructure, which, by construction, guarantees consistency with the laws of thermodynamics. The model describes drilling fluids at a mesoscale level by using two fields, a vectorial, the momentum density, and a tensorial one, the particles orientation tensor. In our current work, where the model is to be introduced, we will restrict to the simplifying case of a homogeneous fluid in the bulk. The use of the new model, properly extended to handle diffusion, to address the flow of drilling fluids in porous media is to be undertaken in future publications. We next present the capacity of our model to predict the rheological behavior of actual drilling fluids. At first, we fitted the experimental data of Hermoso et al. 2014 with our model and provide the best fits, along with the 95% confidence limit for three different mass fractions, 1, 3, and 5%. A very satisfactory comparison of the model predictions with the experimental data is noted, irrespective of the mass fraction and imposed shear rate. As a second test, and perhaps the most vital, we compare against the data of Bue et al. 2012, who provide the rheological data for both the shear viscosity and the first normal stress coefficient. We note once again that the model is able of reproducing the experimental data quite accurately for both material functions. It should be emphasized that none of the usually employed models, like those mentioned above, can capture the first normal stress data, since these models predict a vanishing normal stress. In summary, a constitutive model describing the rheology of drilling fluids is proposed. It obeys by construction the laws of thermodynamics for systems beyond equilibrium. The methodology employed is powerful and flexible, as it easily allows for new physics to be introduced in its building blocks coming from more detailed approaches, such as atomistic or coarse-grained simulations, or more fundamental theories, such as the kinetic theory for the description of hydrodynamic interactions. It allows for the accurate prediction of normal stresses in addition to shear viscosity. This is the take-home milestone of the present contribution. The model presented allows for non-vanishing predictions for both normal stresses, a feature that makes it unrivaled to all other constitutive models routinely employed in the field. If we aspire to optimize drilling operations, the successful predictions of normal stresses for drilling fluids is paramount. It is therefore expected that its use in CFD calculations instead of the aforesaid simplified models will certainly allow for a more reliable and accurate, i.e. closer to actual borehole conditions, optimization of drilling operations.